This is the first section in chapter 13. This is section 13.1, and this particular section is on vector fields. And this is a relatively quick section, which is kind of nice, and it's pretty intuitive as well. Basically, what we have is a field that we are going to assign a number of vectors based on the number of points that we're given. And here you can see in our notes that we have some different vector fields. This first one is showing wind patterns, San Francisco Bay, and depending on the day, we know the wind can change drastically, and so all of these little vectors that you see in this field just represents the wind in that particular area and how it changes. The magnitude is not graphed on these. These are really just showing direction. A true vector field will have the magnitude as well, but you can imagine that if you were to also put in the magnitude of each vector, the length of it, it would be really hard to read the vector field because the size of the vector would kind of get in the way. So sometimes we make these unit vectors so that we're better able to analyze the patterns and the flow and that kind of thing. Here is ocean currents, so another pretty common real world situation. Again, it's just most of those vectors are, it seems at least that they're the same magnitude, just so we can see the actual movement. And then here's another airflow field. Another type that we'll talk about throughout the chapter is a force field, and that would be where you have a vector field made up of force vectors at each of the points in the region. You might have a gravitational force field, that kind of thing. So that's the type of stuff we're going to study in this chapter. But again, section 1 is just vector fields. So let's just take a look at just a couple examples here. We may have a two-dimensional vector field, and again, that's just in a plane. So your vector has two components, just has the components of x and y. Much easier to graph these. And then your other one will be in space, which obviously would have the three different components there. Okay, so we're going to take a look at example 1, and we're going to make a vector field for ourselves. And we're given a number of points here, so I'm just going to walk you through the first couple, and then we'll just fill out the rest. So when we're looking at the first one, x is 1 and y is 0. So when we go up to our equation here, we plug in 1 for 0, or 1 for x, and then 0 for y, and our vector is negative y I plus ij. So in other words, if y is 0, then we have 0 for the first component, and if x is 1, then we have 1 for the second component. So again, we just plug in our values there and get our two components for our vector. And then for the next one, x is 0 and y is 1. So our vector would be let's see, negative 1 and then 0. And then we can just fill out the rest of these, which I'll pause and then do in a second. Okay, so here are the rest of our vectors. So again, we're just taking each component, x and y, putting it into our vector field for x and y, and then we get our two components for our vector. Okay, let's take a look at our very first one. So our first one is 0, 1, that's our vector, and the ordered pair is 1, 0. So we go to our graph, we look at x is 1 and y is 0, and the vector is 0, 1. So we move 0 horizontally and then 1 vertically, and we have this particular vector, and it's pointing in that direction. So again, the horizontal component 0, and then the vertical component's 1. Then we go to the next one, which is going to be 0, 1. So that's going to be here. And our vector is negative 1, 0. So we move 1 to the left and 0 up or down. So that is our new vector there. And then we just continue to do this. So we have negative 1, 0 is the ordered pair. And for our third one here, we have a vector 0, negative 1. So we move 0 units horizontally, and then we move 1 unit down. and then we just continue. I'll pause and draw out a few more. Okay, so I drew out a couple more. I wanted to pause on this one. So this is going to be at 2, 2. So we have the point, the ordered pair 2, 2. So x is 2, y is 2. Put a dot. Then we have the vector negative 2, 2, which means we go to the left 2 units and then up 2 units, and we draw in our vector. Okay, I'm going to continue going, so I'm going to pause again. Okay, so I'm down here. I just finished negative 2, negative 2. So I just did this one, negative 2, negative 2 has the vector 2, so 2 units to the right, and then negative 2, so 2 units down. And then I just have to tweak this and move just a little bit for my last one. My last one is at negative, 2, negative 2, and that vector is positive 2, positive 2. So 2 units to the right, 2 units up, and it looks about like that. Okay, so we're almost done. We just got to do these last 4 right here. So I'll pause and do those last 4. Okay, so here we have all of our vectors that were asked in the table, and we can see that this field prior to us graphing these vectors, we didn't really know maybe what it looked like, but now it looks like it's sort of a circular in nature, where it's sort of moving in a distinct pattern, what it appears to be around the origin. We can actually do a little bit of algebra here and see that this does in fact produce this circular motion. So if we had, for instance, the position vector, let's call it g of xy, equal to just xy. So in other words, we had some sort of vector that came off the origin, x units and then y units. And we were to look at how this interacted with the vector field we just produced, we could take G and dot it with F, the field that we were just producing, and what we would get is the position vector that we created, xy, dotted with the vector field we just wrote out, which is negative yx, and this gives us negative xy plus xy, which of course is 0. So what that means is that if we have a position vector g and a vector from this field, we end up getting a perpendicular. Okay, so this just means that g is perpendicular to f. And in this case, the vector field is actually going to be tangent to a circle. And it's tangent to the circle. So f is tangent to a circle at the origin, so 0, 0, with a radius of the magnitude of g. So in other words, if we had, for instance, a circle that had a radius of 1, you can see that all of these vectors from this particular field are tangent to that circle. And so my position vector, whether it be, like the one I just drew, which is going to be 0, 1, then it is tangent, or it is perpendicular to the field that we just created, because those two vectors have a dot product of 0. So anyway, we can sort of see that this particular vector field is producing this circular motion. Okay, let's go on to example 2. All right, now what we're going to do is we're going to sketch a three-dimensional one, and this is something that's relatively rare. We're not going to really bother with this all that much, but let's make a little table. So let's do x, y, and z, and our vector field made up of x, y, and z. And so let's say we pick, for instance, 1, 0, 1. Okay, well that vector, based on our formula, is just zk, so we get the vector 0, 0, 1. Now, in terms of what this looks like, it's a little bit hard to graph, but if we have our coordinate system in space, so x, y, and z, and let's say that we got it kind of sectioned off here. Okay, so this particular vector is going to be at the point 1, 0, 1. So x is 1, y is, so x is 1 here, y is 0, and then z is 1. So maybe that point is approximately here. And then the vector is going to go 0 units in the x direction, 0 units in the y direction, but then 1 unit in the z direction. So maybe that vector looks like this. It so happens that because of this vector field, if we have the point 1, 1, 1, well, the vector is exactly the same. Now, it doesn't mean it's in the same spot. It's at this new point 1, 1, 1. So that means that x is 1, y is 1, and z is 1. So maybe my new point is approximately here, but the vector itself is going to be the same magnitude, just in a different placement. If we were to pick something like 1, 0, negative 1, then my vector is 0, 0, negative 1. So if we go 1 unit on the x and 0 units on the y, and then negative 1 on the z, so maybe we're about right here, then my vector is going to go 0 units in the x, 0 units in the y, but then 1 unit down along the z, and it looks like that. So we could produce, the whole field just by plotting those points. But again, this is just a simple example in space. Here are some more examples. These are obviously computer generated, and that's kind of a nice attribute to use. You can see all sorts of patterns there, and so most of the fields that we have are going to be computer generated. We won't have to do too many on our own, thankfully. Okay, and then let's talk real quickly about just a gradient field. So one of the most common ones that we're going to use is the gradient field. And just to remind you, the gradient vector is, in this case, the gradient of f. And so our vector is going to be the partial derivative of f with respect to x and the partial derivative of y with respect to x. And of course, if it's in space, then you have all three of your components. And this is going to be the most common one that we'll use when we study vector fields. Okay, let's go ahead and just finish up. We're going to go to example 3. So example 3, we're not going to use Desmos on here, but you can see this graph that's produced over on the right side. So this graph has contour plots of the function f of x, y, and so it's just on a plane, and then it's plotting the gradient field with that. And the important thing to remember here is that the gradient vector will point towards the steepest increasing slope. And so you can see that the size of these vectors, especially up along the edge here, are much larger than the ones that are getting closer and closer to the origin. And all of that stuff just tells us something about the graph. For instance, down here, the gradients are pointing away from the origin. So in other words, we're increasing, if we were to think about this in space, this function f of x, y is increasing pretty rapidly up in the direction of 0, 0 along this plane, 0, 0 for x and y. And then it's going to continue to increase, not at a very rapid pace, but then at a more and more rapid pace as the vectors get larger. So anyway, if we were asked the question, find the gradient vector field, it's a really simple response. The gradient vector field is just the gradient vector f, and it is the partial derivative with respect to x, which is just 2xy, and then the partial derivative with respect to y, which is going to be x squared minus 3y squared. So if we were to pick a point, some point in this plane, we could graph that particular vector, and we would get the vector at that particular point. Then we could pick another point, and we'd graph that vector and pick another point, and so on and so forth. So this vector field will produce, or this gradient vector will produce the entire vector field, which again just kind of helps us determine what's happening with the function itself. One more thing I'm going to write down. I'm going to pause and then write it down, but it's about conservative vector fields. So let me pause and write this down. Okay, so just a little bit of terminology that we need to add in just at the end. So if you have a vector field f, it is called a conservative field if it is the gradient of some scalar function. So in other words, if you have a function that has a gradient vector, or in other words, if you have a gradient field and it came from an original function, an original vector, then that field is considered conservative. This will make some more sense in the next couple of sections, or at least I hope it does. In this case, f is called the potential function for f. It's basically like we're dealing with antiderivatives, and so we're gonna have a gradient field. We're gonna have the gradient of f, and we're gonna find where it came from. We're gonna find the original function for it. Okay, and then at the end here you have a couple examples or a couple answers for our examples that you can see a little bit more completely, especially example 2. This is a nice three-dimensional sketch. Okay, that is section 13.1.